Uh, so this will be the second talk of the series of 3 talks. In this talk, I will be discussing I'll give more details to the examples that Nadi have already mentioned. And also this will serve as an introduction to Shuen's talk. And then also let me thank the organizer for the opportunity to speak here. Okay, so in particular in this talk, what I would like to do is to use 2 examples, one warm-up examples of XY model, and then also the XY plaquette model that Nadi has already discussed to highlight certain features that exist in the continuum field theory, but does not exist in the original lattice model. So let me get started. I'll start with the example that everyone know and love, which is just 1 plus 1D XY model. So I'll be working with a Euclidean time and Lagrangian formalism. So in this case, we will have a 2D Euclidean lattice, and on each side, we will place on that a phase, exponential I phi. And we will allow the phase to interact with its neighbors connected by links. So the actions will be given by cosine of the difference of phis connected by links. So this model, first of all, let's understand this global symmetry. So this lattice model has an exact U1 momentum global symmetry with shift phi by constant. And here I call it a U1 momentum global symmetry following the terminology of Heinrich theory / string theory. So this is really the momentum in target space. It should not be confused with the actual momentum. And when the coefficient R squared are very large, it's very easy to write down the continuum field theory. So the continuum field theory is simply a free field theory of a free compact boson. And so this is its action. And the reason I call it a free compact boson is because I impose an identification that identifies phi and phi plus 2 pi. And it is precisely because of this identification, this makes the coefficient sitting in front of the action, namely R squared, a meaningful coupling. So one may attempt to absorb this R squared into phi, but if we do that, we will change the periodicity into 2 pi R. So here what we have seen is that we really have a 1 parameter family of free field theory of compact boson parameterized by R squared. So let's understand the global symmetry of this continuum field theory. So first of all, this continuum field theory inherited from the original lattice model, a U1 momentum global symmetry with simply shift phi by constant. And this lattice current is given by J mu, and it obeys the standard current conservation equations, namely d mu J mu equals to 0. So in addition to this U1 momentum global symmetry, this continuum field theory also have an emergent winding symmetry. So this winding symmetry was not there in the original lattice model. It only exists in the continuum field theory. And one way to understand this emergent winding global symmetry is to construct its lattice current explicitly. So its lattice currents J mu is given by epsilon mu nu d nu of phi. So it's very easy to see that this currents satisfy the current conservation equation, because if we hit on this J mu, d mu, we will see that the current conservation equation is obeyed identically. So here I call it a U1 winding symmetry following the terminology of string theory / Heinrich theory. And in condensed matter, one can also call it vorticity. So since this is a global symmetry, there should be certain configurations charged under this global symmetry. And so for example, if we put the theory on a circle, then we can consider a winding configurations where phi starts from 0 and then gradually increases to 2 pi. So this is an allowed configuration because phi equals to 0 and phi equals to 2 pi are actually identified. And such winding configurations carries charges under the winding symmetry. So what's more interesting is that this emergent winding symmetry also have a mixed Toph anomaly with the U1 momentum symmetry. So this was already mentioned in Mong's talk. And here I will give a straightforward way to see this mixed Toph anomaly. So the way to see this is to couple both the momentum symmetry and the winding symmetries to classical background gauge fields. So I call them A and A tilde. And under the background gauge transformation, phi will be shifted by the gauge parameter alpha. So that means that all of its derivative would not be gauge invariant. So to compensate that, we will just shift its derivative by a components of A. So here we see that the first term in the action after coupling is simply a modifications of the kinetic terms that we have seen before. And the second term can be understood as coupling the winding currents to the winding background gauge field. So now we have the action after coupling the system to background gauge field. Then the next questions we would like to ask is that whether the partition function is gauge invariant or not under the background gauge transformation in the presence of background gauge fields. So in this particular case, it is actually not gauge invariant. So this signals a mixed tail anomaly between the U1 momentum symmetry and the U1 winding symmetry. And this is really a mixed tail anomaly because here we see that the actions or the partition functions will be gauge invariant when A vanishes or when alpha was 0. And another feature that a continuum field theory has is an exact self-duality, which was not there in the original lattice model. So if we attempt to dualize the original lattice model, we will actually land on a different lattice model. So this exact self-duality in the continuum field theory map the theory at radius r to radius 1/2r, and it also exchanges the U1 momentum symmetry and the U1 winding symmetry. Okay, so let me summarize what I have discussed so far with this warm-up example of XY model. So on the lattice, we have an interacting XY model. And in the continuum, we have a free field theory of compact boson. And both the lattice model and the continuum field theory has a U1 momentum symmetry. And in the continuum field theory, there's in addition to the U1 momentum symmetry, there's a U1 winding symmetry, which can have a mixed tail anomaly with a momentum symmetry. And the continuum field theory also have an exact self-duality, which was not there in the original lattice model. So now I will turn the gear and to discuss XY plaquette model in 2+1 dimension. And we will see similar features that exist in the continuum field theory that was not there in the original lattice model. So this is the model that Nadi has already mentioned, which was first discussed by Perman-Conti, Ballin, and Fisher. And we will consider a 2+1D XY plaquette model and in Euclidean time and Lagrangian formalism. So that means that we have a 3D Euclidean lattice, and we will put on each side a phase, exponential I5. And we will allow this phase to interact. And here is this actions. So its actions, first of all, has a standard, in the time directions is standard, which simply is cosine the difference of phi connected by tau link. And then there's also plaquette interactions in the XY directions, which is cosine of the alternating sum of phi around the plaquette. So this model, this XY plaquette model is natural in the hydrogen theory sense. If we impose the U1 momentum subsystem symmetry, we shift phi by a function of x and a function of y. So if we impose such U1 momentum subsystem symmetry, it will exclude terms, for example, like cosine delta x of phi or cosine delta x squared of phi, and so on and so forth. So again, when the coefficients of this lattice models are large, it's straightforward to write down this continuum field theory. So this is this continuum field theory. And it's also a continuum field theory of a compact boson, and it's also a free field theory. And here we see that the kinetic terms, the temporal components is standard, it's just d tau phi squared. But the spatial derivative terms are non-standard. It is dx dy of phi. And as Nadi already stressed that, precisely because of this double derivative structure, some discontinuous field configurations are not suppressed. And as a consequence, some observables will be discontinuous in this theory. So let's understand its global symmetry as before. So, so this continuum field theory has a U1 momentum subsystem symmetry, which shift phi by a function of x and a function of y. And the Noether's currents of its subsystem symmetry includes two components, j tau and jxy, and they obey a non-standard current conservation equation. And here I call it non-standard because on the right-hand side, we see that it's dx dy of jxy. And it is precisely because of this dx dy structure, well, this makes the symmetry not an ordinary symmetry, but a subsystem symmetry. So in addition to U1 momentum subsystem symmetry, this continuum field theory also have an emergent U1 winding subsystem symmetry, which was not there in the original lattice model. And the currents we have is J tau and JXY. And J tau is the dx dy of phi, and JXY is d tau of phi. It is straightforward to check that they obey a non-standard current conservation equations, similar to the current conservation equation of the U1 momentum subsystem symmetry. And here we see that there's a double derivative structures, dx dy here. And so if we put the theory on a torus, we can construct a non-trivial winding configurations which carries charges under this winding subsystem symmetry. And this is its configurations. So let me stress that, in order to construct a winding configuration, here we necessarily need to use theta functions, which means that the winding configurations is discontinuous configurations. So as you probably can anticipate it, that there's a mixed Toph anomaly between the U1 momentum symmetry and the emergent U1 winding subsystem symmetry. And as before, we can detect this anomaly by coupling both symmetries to appropriate background gauge field. And in this case, the appropriate background gauge field we should use are tensor gauge fields. So, so I will call them A and A tilde. And here they are tensor gauge fields because they have non-standard gauge transformations. So the tensor gauge field has two components, A tau and AXY. And AXY component transforms with dx dy of alpha. So this is a non-standard gauge transformation. So as before, phi transform under the gauge parameter alpha. So all of this derivative will not be gauge invariant. And we can compensate that by adding appropriate components of A. So in the first line, this is the modifications of the kinetic terms. And in the second line, this can be understood as coupling the winding current to the winding background gauge field. So this is our action. And now with this action, we can ask, or we can check whether the partition function is gauge invariant in the presence of background gauge fields or not. So in this case, it's actually not gauge invariant. So this signals a mixed Toph anomaly between the U1 momentum subsystem symmetry and the U1 winding subsystem symmetry. So next, the continuum field theory also enjoy exact self-duality similar to a U1, similar to a 1 plus 1D XY, free field theory of compact boson. And the self-duality exchange mu and mu zero, and it also exchange the U1 momentum symmetry and the U1 winding subsystem symmetry. And this duality was not there in the original lattice model. This is an exact self-duality. So let me conclude with a table that summarizes certain features that exist in the continuum field theory, but not exist in the original lattice model. So on the lattice, we have an XY plaquette model, which is an interacting model. And in the continuum field theory, we have a free field theory of phi. And both the lattice model and the continuum field theory has a U1 momentum symmetry, a U1 momentum subsystem symmetry. And the continuum field theory also has an emergent winding subsystem symmetry, which can have mixed Toph anomaly with the U1 momentum subsystem symmetry. And the continuum field theory also exhibits a self-duality. So what we would like to ask is that, can we find all this phenomena of continuum field theory, namely emergent symmetry, mixed Toph anomaly, and exact self-duality already exist on the lattice model? Can we find all this phenomena on the lattice model? So this will be answered in Shuhan's talk next. Okay, so that concludes my talk.
Great, thanks. It was a nice talk. I guess we should move on to Shuhan because